Hello everyone, I'm Frank and welcome to Frank Puzzles, and this is today's challenging level puzzle. And it's called Halfway There by James Sinclair. And this is the last puzzle, the last challenging or harder puzzle for 2025. So we're more than halfway there. We're almost there, pretty much. But let's get to the rules of the puzzle to see why this is called Halfway There. We have normal Sudoku rules apply, which means in every cell in the grid, place a single digit from 1 through 9 such that there are no repeats in any row. Actually, I should do it this way. Place a single digit in every cell in the grid such that every row, column, and designated 9-cell region contains the digits 1 through 9 exactly once each. We also have exactly one cell in each row, column, and box is a Haver box. So this is the opposite, essentially, of a doubler cell. And the value of a Haver cell, the Haver cells contain the complete set of the digits 1 through 9. That's the reason why I explained the normal Sudoku rules that way, so that it's very consistent, or consistent at least. The value of a Haver cell is equal to its digit divided by 2. That's why it's called a Haver cell. Instead of doubling it, you have the digit, and that's its value. Okay. We have cages, where the sum of the values inside each cage is equal to the small number in the top left corner. And digits cannot repeat within a cage, but values can. So, for example, these 3 digits, or these 3 cells, must add up to 24. These 6 cells must add up to 18, and these 6 cells must add up to 18. Arrows, the sum of the values along an arrow is equal to the value in the connected circles. So, for example, if the value here were, say, a 2 and the value here were a 4, this value would have to be a 6. Because the sum of the values along the arrow is equal to the value in the connected circle. That's an example of how arrows work. For thermometers, the values on thermometers strictly increase from the bulb. So, for example, you could have something like, say, value of 1, value of 3, and value of 4. And this would be valid because the values are strictly increasing. And that's an example of how thermometers work. And finally, we have values in cells separated by a V sum to 5, and values in cells separated by an X sum to 10. So, for example, if this were, say, a value of 3, this would have to be a value of 2 here and a value of 7 here. Because these 2 cells are separated by a V, so they must sum to 5. These 2 cells are separated by an X, so therefore the values must sum to 10. And those are all the rules. If you like to play along, there's going to be a link in the description. And now, I'm going to get started. Let's go. Okay. So, we know you can't have 3 normal Sudoku cell values or digits be in a 2-to-1 ratio adding up to 10. That's just not possible. So one of them has to be a Haver digit. And it cannot... So the Haver digits, Haver values are from 0.5 to 4.5, right? That's 1 divided by 2 and 9 divided by 2 are the minimum and the maximum. So the Haver value is always going to be, essentially, if it adds up to 10, would have to be 1 through 4. So that means the middle value here has to be between the Haver values. And it cannot be a Haver value itself. So this is not Haver value. This is not Haver value. The Haver value has to be one of these two. And it cannot be here. So these cannot be Haver value. To add up a 24, it has to be values of 7, 8, and 9. Again, you cannot have a Haver values 4.5 at most. So these are not Haver values. So Haver value has to be one of these sets. This has to be a 7, 8, 9 triplet. This could be a Haver value of 6 with the 7. That's possible. So this is value of 1, 2, or 3 here. Remaining digits in this box 9 are 1 through 6. This could be 1, 2, or 3. It could be 4 halved or 6 halved. So those work. So 1 through 6, 1 through 6, 1 through 6 in the rest of the box. Obviously, this can't be halved itself. So 6 can never be either of these. This can never be 1 or 2. It has to have a value of at least... Oh, it could be... No, it can't be 2. Even with 1 and 2 halved, that would form 2, but then the problem is you would have to have 2 halved here. So this has to be at least 3. We know at least one of these digits in this cage is halved. 18. Digits cannot repeat, right? But values can. Digits cannot repeat. So that means you could have 1, 2, 3, 4, 5 at minimum. So the sums well, you could have... Okay, so the digits cannot repeat. So the minimum amount for the digits is 21. But you could have 2 halved there. So say you had like the 8 halved and the 6 halved. You could have like 7 halved and 5 halved too. Could you have 9 halved, 9 halved, and 5 halved? So say you had 1, 2, 3, 4. Minimum of with 9 halved, you would have to have at minimum 1, 2, 3, 4, and then 5 halved. So 5 halved is 2.5. 9 halved is 4.5. 2.5 plus 4.5 is 7 at... So you could have 7 plus 1, 2, 3, 4. So it could be 7 halved and 9 halved. So all digits can actually potentially be in the 18 cage. That is possible. This has to have a value of 1 through 4. This is definitely a value of 1, 2, or 3. This has to have a value of 6 through 9 here, so this cannot be a Haver. This is interesting, right? So say if you have 1 Haver. So you can have at most two havers here, and at most two havers here. One of them at least has to have one haver, because you can't have two havers in this box, in these two boxes, and then two havers in these two boxes, because that's three boxes total, right? So one of them has to have at most one haver, which would mean the digits 1 through 6, right? Because the minimum value for having one haver would be 1, 2, 3, 4, 5, and then 6 halved, which is 18. If you try to have something smaller than that, the problem smaller than the 6, that would guarantee at least, say you try to have the 5 halved. You have 1, 2, 3, 4, 6, which is 16, plus 5 halved, which would be 2.5, which is 18.5, which is greater than what this cage has to add up to. So one of these is 1 through 6 here. If it's... it cannot be the thermometers, because values on thermometers strictly increase from the bulb. So because of that, you have to only have one haver, there has to be 6 halved down to 3. But 3 cannot be essentially strictly increasing from 3, which you are guaranteed to have. So this must be the 1 through 6, and must have a haver. And the haver cannot be here, because we know this cannot have one haver here. So one haver has to be here, the other haver has to be here. So this cannot be halved, these cannot be halved. This is halved, so therefore the rest of the row cannot be halved. So this must be haver here, which means this can't be haver here. So this has to be halved here, and it has to be 6 that's halved. So this is 6 here, which means this cannot be 6. This has to be halved. It cannot be 6 halved again. So this is either 8 halved, which would be 4, which can't work. 4 halved or 2 halved. If it's 4 halved, that means this is 2 and 8. If it's 2 halved, it's just... So this cannot be 7. This is 8 or 9. So again, this has to have a 6 and is a haver. This has to be halved. And this has to be halved. And one of these 4 is halved. So where is the haver in column 3? It must be one of these 3 cells. So none of these can be halved. So this could be 1 and 4 or 2 and 3 here. Okay. If this is 2 halved, that's with 9. That's 1 value plus 9 plus 1. If this is 4 halved, that's 2 in value with 8 and 2. So we're guaranteed 2 has to be one of these 2 digits here. So 2 cannot be in the remaining digits in that column. We know 7 has to be one of these 3 cells because it cannot be here, cannot be here. And then the other 8 and 9 is here. 2 is one of these 3. We're guaranteed a 6 halved here. These have to be all unique values because it's consistently, strictly increasing from the bulb. Which means the halved values have to be odd digits. It could be many things, though. This has to be... Can this value ever be greater than 5? You would have to have 6 here, and then this would have to be 7. That's already 13. So I think the answer to that is no, right? If you already have 13 there, you have 4. 0.5. No. You have 6 and 7 as normal digits. You could have 9.5 and 5.5 with 1, 2, and 3. No, 1 and 2? Maybe you could have 5.5 and 3 and 5 divided by 2 and 3 divided by 2. So 6 and 7 is 13. Oh, the problem is one of these two has to be... Okay, so this has to be haver. This has to be a haver. Because if it's not, then this would have to be haver, but that would not be... Well... That's not true. You could have a haver there, and that could be an even digit. That is possible. It could be 8. Could you have 2 even havers then? Possibly. 8 halved and 4 halved would be 12 divided by 2, which is 6. The remaining digits would have to add up to 18 minus 6, which is 12. And 1, 2, 3, 6 works. One, 2, 3, 6, but that would be 4, so you couldn't have a 2. So no, the answer to that is no. If you tried to have 2 halved with the 8 halved, that would be 5. 18 minus 5 is 13 without a 1 possible, because again, the values must strictly increase, so you can't have two values of the same value. So it cannot be that either. So it does have to be 2 odd digits. We tried with... Yeah, we tried with 2 even digits being halved, and that does not work. And that you can think about that normally, right? To add up to 18 with 6 values, each of them being an integer, doesn't work if they have to be strictly increasing, right? Because if it's strictly increasing, it's 1, 2, 3, 4, 5, 6 as integers. Obviously, 0 is not valid, so that would be 21. So you have to have essentially the odd digits be the halved ones. So this cannot be halved here because it adds up to with another digit to add up to 10. So it's not an odd digit halved. So this must be odd digit halved, and this must be odd digit halved. Which leaves these as non-odd digits. This then has to be 1 through 4. And this is 6 through 9. But this has three other unique digits that are smaller than it. So this must be 4. So this is 4 and 6 then. Obviously 4 cannot be here. This digit is between 4 and 3. So we have 4, 3, 2, 1. To be between 4 and 3, it must be 3.5, which is 7 halved. So that's 1, 2, 3, 4, 10, plus 3.5 plus 4.5 adds up to 18. So then this has to be that way. Okay. This 4 eliminates 4 here. So this is 3, this is 2. To be in between, you have to have a 2.5 here. So this is halved, and that's 5. That means these can't be halved. None of these can be halved. Where's the halved then in box 9? It has to be here. So this must be 2, 4, or 6 with 7, 8, or 9. to add up to 10. 2 cannot be here. Where is 2 in box 9? It has to be here. So this is 2 and 9 to add 2 halved, which is 1, plus 9 adds up to 10. So this is a 7-8 pair. 5 cannot be any of these, so 5 has to be one of these two. This cannot be, I guess it could be 1. This can't be 3 because of 3 in the row. This 2 eliminates 2 as being the halved here, so this is 4 halved, which must be with 8 and 2. That eliminates 4 in the rest of the column. Okay. So this is 7 and this is 9, guaranteed to be here. Obviously 9 cannot be here. This can't be halved because of the haver in the row. This can't be halved because haver in the column. No halved here because of haver in the row. So we have a haver here, 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 and here as possibilities. 6 has to be one of these two. 2 and 3. Where are 2 and 3 in column? This 5 eliminates 5 here. Where are 2 and 3 in column 3? Can't be here because of 2 and 3 in the box, so they both must be here. Which makes this a 2-3 pair, which eliminates 2 and 3 in the rest of the cage, because we can't have repeated digits in cages. So this can't be 4. This becomes a 4-6 pair here. Okay. That means, what are the remaining digits in this box? We have 2, 3, 7, 8, 9, right? 2 and 7 cannot be here, therefore this becomes a 3, 8, 9 triplet, which eliminates 3, 8, and 9 in the rest of the column. So this becomes 2, 7 as a pair. This is either value of 4 or value of 3. Either way, it cannot be with 8 or 9, so this has to be 3 here. Right, because value of 4 with 8 is 12. Value of 3 with 8 is 11. And that cannot be a single digit. So we know this is, if this is 3 and 4, this would be a 7, but because of the 2-7 pair, it cannot be 7. Therefore, this must be value of 6, the halved, and this is 4. So that makes that a 6 in value. So this is 6 halved, which is 3, plus 3 is 6. This is not a haver, and these cannot be havers. So this cannot be 3, 7, or 4, 6. Therefore, it has to be 1, 2, or 1, 9, or 2, 8 here. This can't be 2. So this has to be 1, which forces this to be 9 here. This is 4, or it's 8 halved, and it cannot be 4 because of 4 in the column, so this has to be 8 halved. So this is 4 in value here. None of these can be halvers. So therefore that leaves this as a haver. Oh, we've lost my mouse. I'm gonna get some batteries. Hold on, I'll be right back. Okay. And I'm back with my batteries. Hold on. Let me get my mouse batteries replaced. Yay, and my mouse is working again. Okay. So this is halved. This is halved. And this has to be 1 and 3, right? So 1 halved is 0.5 plus 2 halved is 1. That gives you 3 halved, which is 1.5. So then this has to be 1. This is 3. This can't be 9 because of 9 in the row. Where is the 9 in column? 9. It has to be here. So this is 9. We have the digits 1 through 9 in all the halver digits. 1 eliminates 1 here, so this is 5 and 1. This is 4 in value. You cannot have 2 in value here because 2 and 4 add up to 6 and we can't have 6 there. You can't have a 3 in value because of a 3 in the column. You can't have 1 in value because of 1 in the box. So this cannot be 5 in value because of 5 in the column, so this has to be 4. So 4 in value plus 4 in value is 8. Remaining digits in column 5. This 8 eliminates 8 here, so this is 9 and 8. 3 eliminates 3 here. 3 can't be here, 3 can't be here. And these are both non-halved. So it has to have 1 here. And it could be 1, 4 or 1, 5 adding up. But that would force a 5 to be here if that were the case. So this cannot be 1, 4. It must be 1 and 5. So this is 1 and 5 adding up to 6. 4 cannot be here. This can't be 1, 5, or 6, so it must be 3, which means this can't be 1, 3, or 6, so this must be 4. And the rest is probably just Sudoku, actually. Right, 1 can't be in rest of row 3, 1 can't be here because of 1 in the column, the rest is filled out, so this must be 1 here, which leaves that as a 5. Where's the 1 then in row 4? Can't be here because of 1 in the boxes, can't be here because of 1's in the columns, so this must be 1 here, which means this can't be 1 here. This has to be a 7 left in column 9. Where is the 1 in box 1? Can't be here because of 1 in the column, can't be here because of 1 in the row. These are filled out, can't be here because of 1 in the cage. So this has to be 1 here. That gives us 8 ones. We know where the last one has to be. It has to be there. What about 2's? 2 in column 5 cannot be here or here. And it can't be the filled out digit, so it must be here. 2 in box 6 cannot be here because of 2 in the column, can't be here because of 2 in row. The rest are filled out, so this must be 2 there. 2 in box 5 can't be here because of 2, 7 pair in the column. Can't be here because of 2 in the row, so 2 has to be here. And we don't know about these. 3's. 3 in box 5 cannot be here or here, and the rest are filled out because of 3's in the row, so 3 has to be here. In box 3, it has to be one of these 2 cells. In box 8, it cannot be here because of 3 in the row. Can't be here because 3 in the row. Can't be here because 3 in the column, so the 3 has to be here. So that's it for 3. Fours. Box 8 cannot be here or here because 4 is in the column. Can't be here because 4 in the row, so it must be here. Box 4 cannot be here, so it must be one of these two. Box 6 cannot be 4 here because of 4 in the column, so it has to be here. That means this can't be 4, so 4 has to be here. We have 1, 2, 3, 4, 5, 6, 7, 8 fours. We know where the last 4 has to be. It has to be there. Fives. In box 8, cannot be here because of 5 in the row. Can't be here because of 5 in the row. Can't be here because of 5 in the column, so it has to be here. Which means this can't be 5 in box 5, so it has to be here. In box 4, can't be here or here because of 5 is the row in the column, so it has to be here. That means in box 1, it cannot be here because of 5 in the column, 5 in the column here, and 5 in the row here, so 5 has to be there. That gives us 8 fives. We know where the last 5 has to be. It has to be there. Sixes. 6 can't be here in box 4, so it must be there. 6 can't be here in box 6, so it has to be there. In box 3, can't be here, so it must be here. That gives us 6 can't be here in box 8. It can't be here, so it must be here. That gives us 8 sixes, so we know where the last 6 has to be. It has to be there. Sevens. Can't be here because of 7 in the column. Has to be here for box 4. Can't be here because of 7 in the column, so it must be here for box 7. In box 5, it has to be here. In box 8, cannot be here because of 7 in the row. Can't be here because of the 2-7 pair in the column, so it must be there. And it's pretty wide open for box 3, so we don't know for that. 8. In box 7, 8 cannot be here, so 8 is here. In box 8, 8 can't be here, so 8 has to be here. I don't know what I did. In box 6, 8 has to be here, which means this can't be 8. That's 7, which makes that 8. That leaves this digit as a 7. Because we have, right, that's left over. 7 eliminates 7 here. 8, we have 8 eights, so we know where the last 8 has to be. It has to be here. 9s then have to be here, which means this can't be 9, so this is 9. This can't be 9, so that's 9, which leaves that as 9. So all the 9 should be done. 1, 2, 3, 4, 5, 6, 7, 8, 9, right? We have 1, so 2s are left. This can't be 7, so this is 2, which eliminates 2 here. So that's 3, which means this can't be 3, that's 2, which leaves this as 7 and leaves this as a 3. And that's a solution. I don't know. I feel like this is an even challenging level, really. The interesting part was really this one and this one, right? Everything else flowed very naturally. Like, this is obvious. One of them has to have a haver. This obviously cannot have a haver here. And then it was just basically figuring this part out, right? This was the only kind of tricky part. I guess this was kind of tricky, but everything else sort of flowed. It was just, yeah. So, I don't know. Didn't seem challenging to me, but maybe it, I don't know. I'm very used to stuff like havers and doublers and stuff like that, so maybe that's just part of it for me. Anyways, I hope you enjoyed this episode of not Learn How to Sudoku. I hope you enjoyed the solve on Frank Puzzles, and I'll see you next time. Take care.